Okay, Pure Math 2024 exam. Let's get into it. So question 1. Given that f of x equal 4 over x minus 5 and g of x equal to 1 over x, determine the domain for the composite function f g of x. So first, we need to find f g of x. So f g of x is equal to f, and g of x, of course, is 1 over x, so replace g of x with 1 over x. So now we're finding f of 1 over x. So we go to the function f and replace the x with whatever is in the bracket. So we end up with x, replace that with 1 over x minus 5. So that's f g of x. Now notice we have what we call a rational function. So the domain. So now rational functions, notice we cannot divide by 0. Dividing by 0 would be undefined. So it means that 1 over x minus 5 cannot be 0. And if we want to transpose for the x, we'll end up with 1 over x. Add 5 to both sides, we'll get 1 over x is not equal to 5. And if we can invert both sides, 1 over x not equal to 5 over 1. Invert both sides, mean x cannot be 1/5. So that's our domain. X is such that x is a member of a set of real numbers. X is a member of a set of real numbers such that x cannot be equal to 1/5. X being equal to 1/5 will end up with the denominator being equal to 0, and that will make the function undefined. Let's move on. So we have an absolute value equation here in part B. Solve the equation -3 times the absolute value of 2x minus 5 plus 2 is greater than or equal to -4. So I guess the first thing we could do is -2 from both sides. So we'll end up with -3 times the absolute value of 2x minus 5, and 2 plus -2, that will give us 0. So just greater than, and -4 minus 2, that gives us -6. To get rid of its -3, we can divide both sides by -3. So -3 into itself leave us with just the modulus of 2x minus 5. And because we're dividing the inequality by a negative number, we're dividing both sides by a negative number, then the symbol will have to change direction. So this becomes less than or equal to, and -6 divided by -3, that's +2. So we end up with there. Now, so the modulus or the absolute value of 2, so remember the absolute value is just the distance of the value on the number line, the distance from 0, that is. So if this value is less than or equal to 2, then what it means is that the value 2x minus 5 will have to be less than 2. So that will fall in this region. It has to be less than 2, or it has to be greater than -2. Which means here, we solve each equation independently. So if we add 5 to both sides, we'll end up with 2x is less than or equal to 2 plus 5, that's 7. Divide both sides by 2. So x is less than or equal to 3.5. Over here, again, add 5 to both sides, we end up with 2x being greater than or equal to -2 plus 5, that's +3. Divide both sides by 2. So x is greater than or equal to 1.5. And of course, we can combine both inequalities. X is, so the solution, let's put both of them together. X is less than 3.5 but at the same time it's greater than positive 1.5. So that's our solution. So in part C, we're asked to solve a log equation, log x base 5 minus 4 times log 5 base x is equal to minus 3. So notice that the bases are different, so that we first need to get both of them to be the same base. So let's rewrite it. I'm going to convert both of them now to base 5. Right, so what we have is log x base 5 minus 4 times now log this expression here, log 5 base x, we're going to convert it to base 5. So we simply change it. So log, this has become log, change base x to base 5. And 5, but once we do that, we have to divide this thing by log x base 5. So there's a rule in log, that says, if we change the base, for example, log a, so log p base a, if I want to change this to whatever the base, let's say I want to change it from base a to base b, then this is equal to log, and I change from base a to base e, but I have to divide by log, and I was changing from base a to base b, so b, and whatever the base here would come here. Alright, so that's our general rule in log. So notice what I did here. I changed from base x to base 5. So I have to divide by the log of x. So the base here will come here, and the new base, that's a new base. In this case, 5. So let's continue. So of course equal to minus 3. Let's move this. Alright, so what we can do now, we can let log x base 5 be equal to whatever, let's call it y. Alright, so we'll let log x base 5 be equal to y, so we replace this, so therefore we end up with log x base 5, replace that with y, minus 4. Now log 5 base 5, so we log in 5, same base, so that's equal to 1, so this is 4 times 1, which is just 4. So this is equal to 1. So we end up with 4 in the numerator, over the denominator, log x base 5, that's y, equal to minus 3. And now let's try and solve for y. Before we can solve for y, we can times both sides by y, times each term by y, to get rid of y from the denominator. So we end up with y times y, which is y squared. Y times negative 4 over y with negative 4. And y times minus 3, that will be minus 3y. So we have a quadratic. So we can group. So we have y squared. Group this negative 3y over here. That's positive 3y. And we have minus 4. So we have a quadratic. So we can solve by the formula, or we can solve by simply factoring. Alright, so basic factorization there. That's y plus 4, y minus 1. And to solve a quadratic by factoring, we equate both factors to 0. So y plus 4 equals 0, or y minus 1 is equal to 0. So therefore y equal to negative 4, or y equal to 1. Now recall that y log 5 to the base x is equal to y. So therefore we can equate, so therefore log x base 5 is equal to, so therefore log x base 5 is equal to negative 4, that's what y is, or log x base 5 is equal to 1, and then a rule of logarithm again, x that we have here is equal to the base to the power on the right hand side. So x is equal to 5 to the power of minus 4, or same thing, x is equal to the base to the power on the right hand side, which is 1. So x 5 to the power 1 is 5, so x equal to 5. Or over here, x equal to, this is same thing as 1 over 5 to the power of 4, or 1 over 5 to the power of 4, that's 625. 5 times 5 times 5 times 5, or 25 times itself. So we have 1 over 625. So those are our solution. 5 or 1 over 625. Part D, prove that the function f of x equals 3x minus 2 is bijective. And we can do this a couple of ways. We can use it the algebraic method, or we can do it using the graphical method. Let's do the algebraic method. So let f of a equal to 3a minus 2 and f of b equal to 3b minus 2. Alright, so equate. So we can equate f of a and f of b. Now if injective, a should be equal to b. So f of a, that's 3a minus 2. F of b, that's 3b minus 2. We can add 2 to both sides. We end up with 3a equal to 3b. Divide both sides by 3. We end up with a is equal to b. So if f of a is equal to f of b, means that a and b have to be the same value. Right? So hence f of x is injective. We also need to test for surjectiveness or onto. And again, we can also use the graphical method or the algebraic method. Let me use the algebraic method. So if it's surjective, then f of x must be equal to y. So the function here, we can let y be equal to 3x minus 2. And we can transpose for x. So if we add 2 to both sides, we get y plus 2 equal 3x. Divide both sides by 3. So we end up with y plus 2 over 3 is equal to x. Alright, so let's find f of x. So f of x is equal to, since x is equal to y plus 2 over 3, that's equal to f of y plus 2 over 3. And f of y plus 2 over 3, so we go to the function and replace x with whatever is in the bracket. So it becomes 3 times whatever is in the 3 times x, replacing x with the bracket. So it becomes 3 times y plus 2 over 3 minus 2. And 3 into 3, that's 1. So we end up with y plus 2 minus 2, which is y. So we have shown that f of x is equal to y. Hence, f of x is surjective. Or sometimes we use the term onto. Alright, so since f of x is both injective, same thing as 1 to 1, and surjective, it is what we call bijective. Alright, so a function is bijective if it's both injective and surjective. We are now at question 2. The roots of the cubic equation x cubed minus 9 equals 0 are alpha, beta, and gamma. Determine the cubic equation with roots alpha minus 1, beta minus 1, and gamma minus 1. Given that, and we have a long expression there, is equal to 12. Right, so first we need to find, so we have x cubed minus 9, so let's look at, so we have x cubed minus 9 is equal to 0. Notice here, in terms of the coefficients, the x cubed coefficient, we call that a, so a is 1. There's no x squared, so the x squared coefficient is 0, which is b. there's no x, so the coefficient we call as c is also 0, and the constant d, we refer to it as 9. So this is how we label the coefficients for the cubic polynomial a, b, c, d. So the roots are alpha, beta, and gamma. So we know the sum of the roots, alpha, beta, plus gamma, the sum of the roots is negative b over a. Now b is 0 and a is 1. So 0 over 1, that's 0. We also know that the sum product, which will be alpha beta plus alpha gamma plus beta gamma, is equal to c over a. And of course, c is 0, a is 1, so 0 over 1, that's 0. And the product, which is alpha times beta times gamma, is equal to negative d over a. And notice d is negative 9. That's a constant, is negative 9, so negative d will be positive 9, and a is 1. So 9 divided by 1, that's 9. So we want to form a cubic equation. Determine the cubic equation with these roots, alpha minus 1, beta minus 1, and gamma minus 1. Right, so to form this equation now, we need to find, for these three roots, alpha minus 1, beta minus 1, gamma minus 1, we need to find also the sum, the product, and the sum product. Alright, so let's find the sum of these three roots that would form our new cubic equation. Alright, so the sum, let me just put it here. So for a new cubic equation, so for the new cubic equation, the sum, these are the roots, alpha minus 1, beta minus 1, gamma minus 1. So the sum, alpha minus 1 plus beta minus 1 plus gamma minus 1. So if we group the like terms, so we have alpha plus beta plus gamma, and we have minus 1, minus 1, minus 1, that's minus 3. Now we know that alpha plus beta plus gamma is 0. So this alpha plus beta plus gamma, that's 0, minus 3, so that's just minus 3. Let's calculate the sum product. And the sum product would be alpha minus 1 times beta minus 1 plus alpha minus 1 times the other root, which is gamma minus 1 plus beta minus 1. So these are the three roots, alpha minus 1, beta minus 1, gamma minus 1. So we look at, so beta minus 1 times gamma minus 1, so this is sum product of the three roots. Now the question already told us, if we look at here, the question already told us that all of this is equal to 12. So alpha minus 1 times beta minus 1, alpha minus 1 times gamma minus 1, and beta minus 1 times gamma minus 1. The sum product of those three roots equal to 12. So no calculation needed there. And then the final, we need to find out the product of the three roots. So the product, which would be, so product, and the three roots again are alpha minus 1 times beta minus 1 times gamma minus 1. Alright, let's expand. Let's keep the alpha minus 1 and expand the beta minus 1 times gamma minus 1. So beta times gamma, that's beta gamma. Beta times minus 1, that's minus beta. Minus 1 times gamma, that's minus gamma. And minus 1 times minus 1, that's positive 1. And then we're going to expand this bracket now by the alpha minus 1. So alpha times every term in the expression in the second bracket. So alpha times beta gamma, so that's alpha beta gamma. Alpha times minus beta, that's minus alpha beta. Alpha times minus gamma, that's minus alpha gamma. And alpha times 1, that's alpha. And now we're going to take the negative 1 and distribute it to each term again in the second bracket. So minus 1 times beta gamma, that's minus beta gamma. Minus 1 times minus beta, that's positive beta. Minus 1 times minus gamma, that's positive gamma. And minus 1 times positive 1, that's minus 1. Let's see if we can do some grouping now. So we have the product here, which is alpha, beta, gamma. We have the sum, alpha, beta, gamma. So we have a sum, which is alpha plus beta plus gamma. All the other terms are negative. So we can factor out a minus. We have alpha beta. We have alpha gamma. And the final negative term is beta gamma. So factor out negative or negative 1, if you want to call it that. So now we know that alpha times beta times gamma from the original equation. Alpha times beta times gamma is 9. So we can replace alpha times beta times gamma with 9. The sum, alpha plus beta plus gamma, alpha plus beta plus gamma, we know it's 0. So just substitute in these values. And by the way, I'll leave off the negative 1, so let me just put this lower. So we're expanding the group. So this is negative 1. There's no other like term, so negative 1 is by itself. Alright, so again, this was 9, this was 0, and this represents the sum product of the original, and the sum product was what? The sum product of the original here was 0. So the sum product was also 0, and our minus 1, so this is equal to 8. So our new cubic equation should be in the form, so equation is cubic equation, so the cubic equation should be in the form of x cubed minus the sum of the roots times x squared plus the sum product times x minus the product, and that should be equal to 0. Alright, so the solution is x cubed minus the sum, and the sum for the new equation, the sum was minus 3, but it's minus the sum, so it's minus minus 3, that's positive 3, so that's positive 3x squared plus the sum product times x, and the sum product, we found the sum product to be 12. So that's 12x, and we found the product, that's the last thing we found, the product we found it to be 8. So minus 8 equals 0. So that's our solution. X cubed plus 3x squared minus 12x minus 8 equal to 0. The function f of x equal to x cubed minus px squared plus qx minus 5 is divisible by 2x minus 1 and has a remainder of 7 when divided by x minus 1. Calculate the values of p and q. So p is the x squared coefficient there, well, minus p, and q is the x coefficient there. So we are told it's divisible by 2x minus 1, which means that 2x minus 1 is a factor. So therefore, f of half should give no remainder. So f of half should be 0. Also, we are told there's a remainder of 7 when divided by x minus 1. So f of 1 should give a remainder of 7. And in terms of how we get the x minus 1 and the how we get 1.5, if you equate 2x minus 1 to 0 and solve, you get 2x equal to 1. Divide by 2, you get x equal to half. So f of half leaves no remainder since it's divisible, so we have 0. The other one, x minus 1, if you equate to 0 and solve, you get x equal 1. Hence why we're using these values, half and 1. Alright? So f of half is 0, f of 1 should be 7. That's remainder slash factor theorem combined. Alright, so f of half means we're going to replace each term, each x term with half. Alright, so 2x cubed becomes 2 times half cube minus px squared, so minus p times half square plus q times half minus 5. That's equal to 0. Let's see if we can simplify this now. So half to the power of 3, that's half times half times half, that's 1/8. And 1/8 times 2, that's 2/8, so that's a quarter. Minus half square, that's half times half, so a quarter, so a quarter p, or p over 4. This is what? Half q, or q over 2, minus 5 is equal to 0. And of course, one thing we could do to get rid of the fractions, we can multiply by the LCM, which is 4, so we can times each term here by 4. So 4 times a quarter, that's 1. 4 times p over 4, well, that's negative p. 4 times q over 2, that's 2q. And 4 times minus 5, that's minus 20, equal to 0. And of course, we can group the constants on the right hand side. So we have minus p plus 2q equal to, you bring over these constants, you get positive 20, negative 1. So you get 20 minus 1, which is 19. So that's one equation. It's called equation 1. The other one, f of 1 equal to 7. Let me put it a little bit higher so I can get more space. F of 1 is equal to the remainder 7. It should be more straightforward since it's 1. 1 to n power is 1. So substitute 1 for the x is 2 times 1 cubed, that's 2. Minus p times 1 squared, that's p. Plus q times 1, that's q. Minus 5 is equal to 7. And of course, again, we can group the constants over on the other side, right hand side. So what we have is minus p plus q equal to, and I bring all these constants. This is negative 5. Add 5, we'll get 7 plus 5, that's 12. And bring over the 2, you get 12 take away 2, that's 10. So when the constants are grouped, we'll get with negative p plus q is equal to 10. So we have a pair of simultaneous equation here. Alright, so we have negative p plus q equal to 10 and negative p plus 2q equal to 19. We can solve simultaneously. So now put in negative p plus q equal 10 below here. And we can subtract. This is equation. Subtract. Right, so minus p minus negative p, that's negative p plus p, which is 0. 2q minus q, that's q. 19 minus 10, that's 9. So q is 9. And then to get the value of p, we can simply plug it into the other equation. So if I substitute it into this, what I'll have is negative p, replace q with 9, so plus 9 equal to plus 9, so replacing q with 9, right? So plus 9 equal to 10. I can do some little rearranging now, so bring negative p over here is positive p, bring a 10 over here, it's 9 minus 10, which is negative 1, so negative 1 equal to p. So our solution, q is negative 9 and p is negative 1. Part C, let p be the proposition that if n's cube plus 3 is odd, then n is even for all integers n. Provide a proof by contradiction for this proposition. And we're given a hint there. Let n cube plus 3 be odd, and assume that n is odd. Assume that assumption that n is odd is incorrect. Okay, so proof by contradiction. So the first thing we want to do is, so it's difficult to start from n cube being odd. Let's start from the right on the other side. So in terms of, let me call this a conditional statement. So if p, then that. So I'm going to call this p and then q. So the first part of the statement and then q. Now we know that the contrapositive is also true. So p, we know that p imply q is logically equivalent to not q imply not p. So one approach you could take, before we get to the contradiction part, one approach you could take is rewrite the statement. Alright, so here's the statement. If n cube plus 3 is odd, then n is even. So we can rewrite the statement, the contrapositive. So the contrapositive would say that. So this is what we'll prove instead. So I'm going to prove that the contrapositive of this, if n is, and we're taking the opposite, is odd, then n cube plus 3 is even. So that's an equivalent statement to the original statement that we are given to prove. Alright, so let me ignore this for now. No, so this is what we're trying to prove. If n is odd, then let's switch this around and read from the right to left. If n is odd, then n cube plus 3 is even. Now, if we're going to prove this by a contradiction, we just need to change one of them. All right, so we're going to, the contradiction. We will attempt to prove that if n, and I'll change this, is even, so let's change that, then it doesn't matter which one I change. I'll change the first one. If n is even, then n cube plus 3 is even. So I'll just change one of them. So, if n is even, let n be equal to 2 times k. Of course, k is some integer. So, let n equal to 2k. Therefore, n cube plus 3 will be equal to 2k cube plus 3. So we end up with 8k cube plus 3. And of course, we can rewrite positive 3 as 2 plus 1. And of course, for the first two terms, we factor out 2. So that with 2 equal to 4k cubed plus 1 plus 1. And this, of course, so we have 2 times a value plus 1. So what we have here is a even number. Sorry, odd number. An even number plus 1. This is an even number. 2 times a value is always an even number, whatever the integer is. And if you add 1, you're going to get an odd number. Alright, so this is odd. But if you notice, it's supposed to be even. So therefore, we end up with a contradiction. So therefore, a contradiction. Hence, the original statement holds true. And what was the original statement? Original statement is this statement: if n cubed plus 3 is odd, then n is even, or the contrapositive. Alright? Which is saying if n is odd, then n cubed plus 3 is even. Let's move on.